We just talk about convergence of gradient descent. Now we talk about projected gradient descent. For NEF, no longer is a simple minimized QP subject to x larger than 0. Now it's NEF. And now you see, wow, my gosh, this is so ugly. Yes. So let's recap what is the constraint and unconstrained. Unconstrained means any x is okay. Constraint means x has to be inside a set Q or set C. This is an example. Minimize least square subject to x cannot be too large. Or one norm cannot be too large, or two norm cannot be too large. Okay? Now, here's something. You can solve this by ADMM or Lagrangian multiplier, which you see I use so many red color thing to describe. Actually, I don't like Lagrangian. I like Lagrange, but I don't like Lagrangian. Okay? And you should always go to this because it's simple. I'm not saying this is mathematically wrong. This is mathematically correct and actually mathematically very exciting. But to really understand why Lagrangian is good, you need to understand something called French conjugate. And usually when people talk about Lagrangian multiplier, they don't talk about conjugate. And people lost the deep meaning of why Lagrangian is good. So therefore, this approach should go to when you talk about conjugate. This is my opinion. Okay? And now let's talk about how do we solve this. Well, we do gradient descent. Okay, not going to talk much. But what happens if I have a set Q? I need to make sure X is in Q. These are the settings. F is convex, deep shape, continuous, blah, blah, blah. Q is convex, blah, blah, blah. Okay, we don't talk about it anymore. So now this is the idea. What is the gradient descent? Gradient descent. O point, step size, gradient. What is projected gradient descent? O point, step size, gradient. After that, you project to Q. And that's it. So basically, projected gradient descent is just gradient descent plus a projection. Then what is this P thing? This P thing on a particular point, this is a particular point, this is not whatever x, this is a fixed x, is to solve this optimization problem. So projection step is an optimization problem. So you are casting projection to minimize this. And important, this is find the x in Q closest to your x star. That's the meaning. So this is, okay, these are details. This is the idea. So you have a set Q, this is your x0. Here's the idea. If I have this situation, finish. Why? Because the smallest distant point to x0, where x is in Q, what is the solution of this? Itself. Because x0 is already in Q, then which x is closest to x0? X0. That means if you have this case, the answer is x0. End of story for the projection. More interesting case is this case. What is this case? x0 is not in Q. If x0 is not in Q, you want to find the x in this Q that this is the smallest. This is now the geometry. What is this? Equation of circle. So you draw a circle. What is this? This red circle means this is a circle where a set, I call it B red, okay, B red. What is B red? It's all the x that this is 5. So this is 5. What is this blue? This blue is another circle. I call it blue. It's all this thing, x minus x0, that the radius is 10. So this is 10. This is the two norm thing, right? So what is the minimizer of this for the x inside here? You find an unknown radius r such that x minus x0 is exactly r, and this x has to be in Q. That's the solution. So this is the idea. This is a solution when this distance is smallest, and this x is exactly in the Q. So the idea is, you have this thing, you grow a circle, grow a circle, grow a circle, until the circle is as big as it just touched the Q, then this point is the solution of the projection. And this is the idea of the projection. This is what? Projecting onto a convex set. This is the idea. And you can prove this is always in the boundary. Why? Okay, these are details I talk about a little bit. I can tell you this is always not INTQ, interior Q. Why? Because suppose this is a Q, and you project your x0 to here. By definition, this y in interior of Q topology means I have a ball here. Then why not I project to the boundary of the ball? It's smaller, the radius. So that means I have to be in the boundary. I cannot be interior. Because in the boundary, the definition of boundary is I have a ball, half of them is in the Q and half of them is not in Q. Right? So therefore, it must be on the boundary. It cannot be here. If I'm here, then why not here? If I'm here, then why not here? If I'm here, then why not here? You see, I can keep going on forever. In the end, I will touch the boundary. So that's why you can never be in the interior. Always on the boundary. And because always on the boundary, it's so interesting that this is always 90 degrees. So therefore, this is called orthogonal projection. Orthogonal projection. And this actually have deep meaning. Why? What we are doing in the projection? We are doing a projection by what? X minus x0 arc min x in Q. This is 2 norm, right? What happens if I have Bradman divergence? Then I will have irregular projection. But the same idea holds. So if your geometry of this thing is a diamond, actually you should not do orthogonal projection in the Euclidean sense. You should project it using diamond geometry. Then you replace this by Bradman. Okay, this is the idea. But anyway, so now here's a formula many years ago called Bourbaki-Cheney-Goldstein inequality. What the heck is this? It basically this. What is this? This is your Z. This is your Z. You project it onto the set C. So this is the point. So this is the point. You have any X in C. This is the blue X. This point and this point subtract each other, give you a line. This point and this point subtract each other, give you a line. These two lines, always the angle is larger than 90 degrees. And this one is what? It's the normal cone argument. Do you remember normal cone? Normal cone is, I have a point here, this is the cone, which is the same kind of angle thing, right? This is the same thing, okay? This thing comes, I don't know it's before normal cone or after normal cone, I don't know which is earlier, but these are very old anyway. Okay, so this is the idea. And this projected gradient descent is actually a special case of proximal gradient descent. Proximal gradient descent is this term become any G. So that's why we study proximal gradient descent. But now we're talking about projection later, okay? So now again, convergence. And this convergence is slightly different. It's ergodic. We don't talk about point-wise convergence. We talk about ergodic convergence. So what's that? So this is the picture. So what is sequence convergence? Sequence convergence is I have a point here. Go to, let's say the solution is here. So sequence convergence is I have here, 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 I have here. So go here, go here, go here, go here, go here, and then you then go to here. What is ergodic convergence? Let's say I have a point, solution is here. So ergodic convergence is like this. I have a point here, and then suddenly go to 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 here, and then what? And then I keep randomly join. Now you should feel what is ergodic convergence. Is what? The past k point take an average, this thing converge. So if I do this, the first 5 iterate is this shape, I have 5 points. This 5 iterate is this shape, I have this 5 points. This 5 iterate, I have this shape, I have this 5 points. The centroid of this shape is here. The centroid of this shape is here. The centroid of this shape is here. So it's the centroid converge, not the point converge. And this is a classical technique used in stochastic gradient descent. So convergence is centroid of a bunch of points moving toward the limit point, not the point. So ergodic is relaxation of pointwise convergence. And for projected gradient descent, you have this. Why? Why we have this? Now let me explain. Because you can have this crazy thing. Imagine, I want to go here. Imagine I will go here. This is my x infinity. Now, I have here, and this is my C. This is my C, okay? And suppose the gradient flow or gradient vector field is always point to this way. Now here's a funny thing. First, I do gradient descent. Go to here, because gradient point to this. Then I projection, I go to here, okay. Then what? Then the gradient vector field, let's say, I make a mistake, should be here. Then it will point to here. And then projection go to here. And then gradient again point to here, and then projection go to here. Now you should see what I'm talking about. Your sequence actually is, it's not like the yellow. Yellow is like monotonically getting closer to this. your sequence here have this bouncing effect. That means what? That means sometime you go to here, you are getting further away from here. Because this process can make this line longer than this line. But what we can guarantee, the average of this 4 points, the centroid here, the average of this 4 points, the centroid here, the average of this 4 points, the centroid here, the centroid is actually getting closer. So that's why we talk about go there. It's possible that the projection will make your point go further away, right? But if the centroid is getting closer, then in the end, what? In the end, this shape becomes very tiny, that the 4 corners become 1 point, then everything converges. So this is why convergence of projected gradient descent is slightly different. So we prove this. Do we have time? No. Maybe we talk about it tomorrow. Okay, I'm hungry.